Hello everyone! Today we will discuss one of the most important discoveries in physics. Did you guess it? I'm talking about electricity. Magnetic phenomena has been known for centuries, and thanks to that we have had compasses for more than 800 years. But electricity took us a bit longer to understand. We've been aware of things such as electric shock for centuries, yet it is only in the last 500 years that we have more rigorously formulated our understanding of electricity. It is hard to say when electricity was discovered, as we discovered its phenomena over the years. Physically, we often consider electricity as something to do with electrons, and the electron was the first fundamental particle we discovered in 1897 thanks to J.J. Thomson. This marked the beginning of a new era of particle and quantum physics. What is electricity? That's the topic of today. Electricity is a cornerstone of modern civilizations, and without it you wouldn't be watching this video today. Electricity is one of the most important needs for society to power our electronics and light the streets at night. Electronics today are in everything from cars to refrigerators, and nothing would work without electricity. In the previous video we discussed magnetism, and we know that magnetic objects are dipoles, thus there is a north and a south pole. Electric objects are different, they can have monopoles of either a positive or a negative charge. Per convention, electrons have come to be defined as negatively charged. But this is a human convention. In principle, we could have defined everything the other way around. Most importantly, electric charge is a fundamental property of many particles. Fundamental particles like electrons are always charged or neutral if they're not affected by the underlying electromagnetic force. This doesn't mean that we can't make electric dipoles from the monopole particles. Take for example water, it has an electric dipole. It's positive near the hydrogen atoms and negative near the oxygen atom. Electric charge is a fundamental property of matter. As mentioned, we can have a positively charged particle and a negatively charged particle. Similarly to magnetism, a positive and negative charge attract each other in the same way north and south poles attract each other. In the same fashion, two like charged particles repel each other. This we can understand in terms of field lines of the electrostatic field formed by two charged particles. By definition, the field lines of a positive charge is outgoing and incoming for a negative charge. If we take two oppositely charged particles and draw field lines, we can draw a connecting line coming from the positive to the negative charge. If we take two negatively charged particles, we cannot draw connecting lines because both have incoming field lines, not outgoing. Similarly, two positive charges have only outgoing field lines, and again we cannot connect the lines between the two. This signifies repulsion between like charged particles. Electric charges form electric fields, similarly to how massive objects form gravitational fields. More precisely, the electric field is a vector field, thus it has a direction where you get pulled. This direction depends on the charges, and this is different compared to gravity, because in gravity you only have attraction between massive objects. Since objects can not have a negative mass, it might not be a surprise that we can define the force of two charged particles in a very similar way to Newton's law of universal gravity, where the force F is equal to K times Q1 times Q2 divided by R squared, where K is a constant and Q1 and Q2 are the two charges separated by a distance R, which is squared. Again, the force will be attractive if the charges are opposite and repulsive if the charges are like. This equation for the force is called Coulomb's law, and we see that as the distance between the charges increase, the force also decreases. We know electricity is important because it powers the world. It gives energy to our devices such that they become useful. The amount of electricity one can use is associated with the electric potential. Thus, an electric field has some electric potential energy. Consider a battery. It has a plus and a minus pole. What is an important characteristic of battery? It has a potential difference between the positive and the negative pole, and this we can make use of. We commonly call the potential difference for voltage, and different batteries provide different voltages such as 5 volt or 12 volt. This is also related to how powerful a battery is. Another aspect is current, or how much flow of electricity a battery provides. In this way, the power of the battery is given as E is equal to Vi, where E is the power or energy per second, V is the voltage, and I is the current of the battery. If you have more voltage, you have more energy, and likewise a higher current also gives you more energy. We can understand the concept of current and voltage a bit like a water mill. Water is the current and voltage is the pressure. If we have a low voltage and a big current, we can run the mill for a long time. But the mill does not spin fast, so it's limited in how much it can pull without stopping. If we increase the voltage, it will be like increasing the flow of water and thus making the mill run faster. In this case, the mill can do more work. The downside is that if you have limited water, you will quicker run all the water through the mill and run out of water. This is like a battery running out of power. This is also why a battery with a higher voltage will in general not give you a longer lasting battery unless the battery also provides a lot more current. Now, what is current physically? A direct current must have a direction, and since electrons are generally associated with electricity, we often associate currents with electrons. But it could be anything charged. Per definition, the current runs from the negative to the positive pole. So you might think that it means that the electrons is running all the way from the negative through the circuit to the positive pole. While this isn't entirely inaccurate for direct current flows, it is not that simple. In a closed circuit, electrons do move around, but not very fast. Depending on the current and the voltage, we might be talking about centimeters per hour. What is important is that the electric energy is transferred at the speed of light. That's why a lamp turns on immediately after you flip the switch. Again, the battery is like a dam. When you have no more water to send through the mill, you can't do more work. When the negative pole cannot send more electrons and the positive pole cannot absorb more electrons, the flow stops. The electrons does not go around in circles. They can at most go from minus to plus. I hope you got a better understanding of the concepts of voltage and current and how electrons do not really move that much, but electric energy nevertheless moves very fast. In the next video we will look a bit more into the topic and look at Ohm's law. If you have any other topics you would like to see covered, please let me know in the comments together with any other feedback. As always, please like and subscribe if you like the video and want more, as it helps to promote the videos. I hope to see you next time. Stay tuned for more videos to come.